everyone. My name is Ahmed Kamal. I'm a third-year student in Cardiff University doing electrical and electronic engineering. I'm here today to talk to you about the project that I chose for my dissertation for this year, which is RF beacon and spectrum monitoring system components. Now, what is this project about? This project is inspired by the UK Microwave Group. And the plan is that they were planning to set up the RF beacons RF signal beacons all around the UK, like transmitters and receivers, to monitor the microwave signal around the country. So to take part in this project, I am going to build a RF signal transmitter that can work at various frequency bands. In order for this RF signal transmitter to work, I need to configure an RF signal generator. And for this project, we've chosen the ADALM Pluto device. And by configuring these devices, we can send signals, informations and messages, basically. And then after that, we need to modulate these generated signals using FSK, frequency shift gain. And lastly, I need to design and build a filter, a bandpass filter, more specifically to filter out all the noises and harmonics that are going to be present in our transmitted signal. So as we all know, RF signals are just a wave of a form of energy that can be considered as electromagnetic waves, and they can propagate either in solid state wired communication, or they can propagate in space wirelessly, as we all use it heavily in wireless communication. And to generate these RF signals, we're going to need a frequency synthesizer. And the frequency synthesizer basically produce RF signals at a very different range of frequencies. And for this project, like I said earlier, we've used the ADALM Pluto device. It's a very handy device, very small. It generates signals between 300 kilohertz to 3.8 gigahertz. It's very configurable. It's used heavily in base stations, as it is very configurable, and it is made by analog devices, like we can see, and it's made by analog devices and. It's made by analog devices, and we can use it. It is based on software-defined radio technique. So the idea behind software-defined radio is that we need to move as much of the radio functionality into software-based system. So instead of using hardware components like mixers or modulators, we can just implement these on software-defined radio. And for that, in order to build our system using software-defined radio, we've used the free toolkit GNU radio to work alongside the ADALM Pluto. And the chosen GNU radio because it just allows us to have the framework and the tools that we need to produce our RF signal system. So, and this is what GNU radio looks like. This is what we call the flow graph of GNU radio, and it's built of many blocks. Each block has different functionality depending on what you want to do. And firstly, to start the project, I needed to make a continuous wave signal. Like we see here, we have, we can't see on the map here. So we have this signal source that generate our sinusoidal wave. The Pluto SDR sync basically is the transmit side of our Pluto ASDR, either ADALM Pluto. And then in order to test the sinusoidal signal, we can connect the Pluto SDR source, which represent our receiving side on the frequency synthesizer. And then we can look at the frequency sync. Here on the blue, we can see that is the transmitted signal, and the red is the received signal. But from this graph, we can't really tell much, so I had to implement the two-tone test to measure and confirm the linearity of the signal sideband signal. Two-tone test is based on generating two signals of different size, but not harmonically related. So We have two signal sources, again, two sinusoidal signals, one at 250K, minus 250K. We add them together, again, connected to the Bluetooth SDR sync to check the output of the transmitter. Here, the two-tone test is based on changing the amplitude, the frequency, and the gain of the signal, and then you can study out all the harmonics and noises. So yeah, so the two signals we've used, then we're gonna see it is 975 hertz and 1250 hertz. And then we looked at the spectrum analyzer. Here we can see our two signals. There and here we have our two signals. They're nice, a bit clean, but there's a lot of noises. In the middle, we have local oscillator leakage, and it's a property of the mixer. And basically, it tells how much energy that is coming from the local oscillator that is transferred into our transmit side. And it is compared to our signals is very small, so it's always going to be there. So we can't do anything about it, but it's very small, so it's all right. We can deal with it. And yeah, we have a lot of other noises coming from the Bluetooth SDR itself, from the spectrum analyzer. And to study our harmonics, we have another signal that you can see. That made it hard for us to actually spot which one is our harmonics and which are the noises. So what we did is to by changing the amplitude within GNU radio. By changing the amplitude within GNU radio, we could see that some of the signals are actually moving with the amplitude, and this tells us, okay, this is the noise, and it helps us basically differentiate between the unnecessary noise and the harmonics that we need to study. So the whole point of doing this test is to actually build a bandpass filter to remove all the harmonics and the signals that we don't want and the noise. So here we've used ADS. We've used design guide on ADS. It's basically very easy. It makes it very easy for us to design a bandpass filter. All we need to do is just write down the specification, put down the specifications we need for our bandpass filter, and boom, it gives us our bandpass filter. It gives us all the components. One problem with this is it gives us theoretical numbers. It doesn't actually give us practical values of the lumped elements that are on this circuit. So next challenge for me is to look at the practical components, compare them to our theoretical ones, and then simulate this one, simulate the theory, simulate the practical, and try to get as close to the response to the theory. That's with the bandpass filter. And then now we generate a continuous wave. We have a initial design for a bandpass filter. We need to actually generate the message that we need to transmit. So in order to do that, we use Python language. And Python, the reason we've chosen Python language is because GNU radio can actually understand, is written in Python language. So it makes our life easier. So for this project, we have used 8-letter message, basically that tells us maybe the location, for example. And we've done a couple of processes to change this 8-letter message into an array of bits that we can transmit. So first thing, we've used the source encoding. What it does, it compresses information. It compresses the information depends on the type of the information. And it decreases the redundant bits within our signal, with our generator signal. And but these redundancies make it very difficult for us to spot the errors. Makes it very difficult to spot the what's it called? Sorry, I forgot the word for it. Make it very difficult to spot the errors and basically the errors within the bits that we're gonna send. So we used a convolution encoding technique, which makes use of forward error correction. And the point for using that is it produces error correction within our array of bits to correct. The more error correction bits we have, the easier the code can be corrected, the data. Next, we moved into interleaving encoding. Interleaving encoding. So these what's it called? So the interleaving encoding basically mixes up all the array of bits that we have to separate all the corrupted bits, and then again forward error correction can come again and then correct our signal bits. Lastly, I have merged our signal data after all of this with the synchronized vector, and then I could have a signal that is ready to be transmitted. I can show you on GNU Radio itself. So here, this is PI4 beacon encoder is where I've coded all this code. Message edit is where I can actually type in the message, and then it converts it to the array of bits. Character to float, and then time sync is going to show us the data on a graph, basically. So I can write in any letter, any message of eight letters, 1, 2, 3, 4, 5, 6, 7, 8. And then we can see at the bottom here, instead of the 8-letter messages, it sends out all the equivalent bits of array from 0 to 3. Back to the slides. So there we go. So lastly, I need to modulate this data that I've sent. So I'm going to use frequency shift gain modulation. The reason for using frequency shift gain because it's the standard modulation for this type of PI4 beacon. So, and that's that. So next, that's it. That's what I've done so far in my project. So next thing I'm going to do is achieve signal modulation within GNU Radio itself, and then fabricate that bandpass filter I was talking about earlier, and then test the whole system, and then see if it can actually transmit and it works. And we're going to test it by, Derek here is building a receiver, so my transmitter, and then we're going to use Shem's power amplifier, and then we're going to try to see it on the receiver and see if I actually received the message that we've transmitted. And that is it. Any questions, please?